Okay, so now we've used Maple to solve a problem. This is kind of the way you're going to do it. So let's move on and talk about kind of the next concept. Again, this is, I think, mostly review for some of you, probably useful review. But what I want to do is the second time we're thinking about this, this idea of thermal resistance, maybe we can think about it in a more practical sense. Okay, so we'll see what I mean in a second. Okay, so we just went through and solved this problem. We solved this expression for temperature for this specific problem. And if we kind of look at our solution for that, we often want to understand, what is Q dot, right? So what is Q dot for this? How does Q dot relate to temperature directly? So if we solve for Q dot, meaning we evaluate the expression for Fourier's law, right? dt, let's say dr in this case. So if we're solving for that, we need to take the derivative, right? We need to have our temperature expression, take the derivative and evaluate it. By the way, you can do this really easily, again, in Maple. So let's look back there and actually use that to do that. So let's just calculate Q dot. So Q dot is equal to, let's see, so we have minus K, right, times 2 times pi times R times L. By the way, this here, small thing, is capital PI. So if you use lowercase pi, it's the actual number pi. Capital PI is the symbolic pi. So like 99% of the time you want capital PI. Okay, so Q dot is that. And then we have to multiply by diff of T of R, it's TR. Let's see, which was a TS, right? Diff of TS with respect to R. Okay, so if we evaluate that, we get our derivative. Right? So this is the solution here for Q dot. Notice, by the way, that nothing in there has R in it. Right? We have R out, we have R in, but Q dot is not a function of R. Okay, that makes sense because, well, there was no place for heat to go except for in the domain and out of the domain. So it's not changing as a function of R. Okay, so anyways, we have our Q dot. It's in terms of these boundary temperatures TC and TH. Okay, so we can take this idea and go back to our notes here. Okay, so we evaluate this. We come up with this expression here, right? Q is this function. The idea behind thermal resistance is that if you just want to understand kind of the basics of a problem, you just want to get a handle on what's important in a problem, thermal resistances are really the best way to do that. Okay, and where does this idea of thermal resistance come from? Well, if we look at the electrical analog, so if we look at a circuit, a really simple circuit, right, so let's say we've got 2 points on a wire. Okay, there's a high voltage, VH, and there's a low voltage, VL, and there's a resistor, right, an electrical resistor between these 2 voltage points. If you have this voltage with a resistor, you're going to have current across it. We'll call that current I. Okay, so in circuits, the equation for this, so the representation of how I relates to these things would be I is equal to VH minus VL over RE, right? This is the relationship between these things. So we have the electrical kind of analog here is directly applicable to heat transfer. So for heat transfer, you can also represent, if you have a surface, a domain with, say, 2 temperatures, right? Say TH and TC, and then you have some impedance to the heat flow, which we'll call R. You would have heat flow across that, right? So the relationship would be Q dot is equal to TH minus TC divided by R, right? So there's this kind of direct analog between these 2 things. I mean, this is, again, is not that profound of an observation, except that if we start calling R, whatever it is that's multiplying our temperature difference, our potential, then we can compare R's, right? We can say, for this conduction problem, I have a conduction R, and I have a convection R, and I have a contact resistance R. And what's the magnitude of the values of these R's? And just by looking at that, we can really quickly get a handle on what's important in the problem. Right, half the battle in this class and at this level is trying to figure out what's important and figure out how to deal with that. Okay, so this resistance approach is kind of a tool that you have. And as we talked about it in like 364, it's more like a methodology. You just follow the methodology. Here, it's more a tool to help you assess other things in the problem. Okay, anyways, that was a bit of a side note. So let's kind of write out our idea here. Okay, so if we have Q dot, and our Q dot expression for this problem we solved for was what we see down here. It was 2 pi LK over ln of R out over R in times this potential TH minus TC. Then what are we calling the resistance in this? Right? The resistance in this is going to be this guy here. By convention, we say that resistance goes in the denominator. So actually this becomes 1 over our resistance. So now we have this convenient expression for the resistance in the cylindrical geometry. Anytime we have a cylindrical geometry and we want to compare the resistance due to conduction to something else, we can just pull out this formula and use it, right? It's important to note though, remember what we did when we were deriving. When we were deriving this expression, we said there is no generation, right? And there is no du dt. So if you have a situation where there's generation in the domain, or there's non-steady state behavior, du dt is not equal to 0, resistance is not valid, right? It can be valid as a tool, but it's not going to get you fully the answer, okay? In the assumptions that we made, this actually gives you the correct answer. Okay, so we end up deciding that R is equal to this, 1 over this here. We can move on and look at other geometries, right? If we have a plane wall, we looked at cylindrical. If you have a plane wall, the plane wall resistance would be L over KAC. Right, here's our cylindrical solution here. If you have a sphere, this is what it would be. People often get tripped up on these things. So L and AC, especially for plane wall. So let's kind of draw what those are real quick. So if you have a plane wall, let's say it looks like this. Draw it. You have heat flow in this direction. Let's call this positive X. What we're saying, let's kind of draw this in 3D, I guess. Right, so what is L? So in this case, L is this length here. So this length L is how far you have to go. Sometimes people call it thickness, right? So you would say thickness over KAC, L over KAC is the same thing. And then what is AC? Well, AC is the heat that's available for, or the area that's available for heat flow. So in this problem, that would be this plane would be AC. All right, make sure you sort those out when you're applying it. I think the other ones are relatively straightforward. Okay, right. So these are the resistance formula you're going to use for conduction. Like I said, though, there's ways to compare different resistance formula for different phenomena. Okay, so thermal resistance for convection. Convection is what you see here. So you have some fluid moving over a wall. You have heat convecting from the surface up, right? And this is our surface, and at that some temperature. So we would write this in terms of for convection, convection in terms of temperature as the heat transfer coefficient, H bar. Right? This usually has units of watts per meter squared Kelvin, times the area, right? The surface area. By the way, what's the surface area? It's this, right? Maybe it's obvious, but it's the area that's exposed to the fluid. Okay, and then times the driving potential. So that would be Ts minus T, we call it infinity in this case. Okay, so what is our resistance? Well, it's just 1 over this, right? 1 over our convection is that. Okay, by the way, this is called Newton's law of cooling. I don't know if you'll ever use that again, that's what it's called. Okay, and then for radiation, similar kind of thing. This hopefully is review, Q dot radiation. Right, the expression for this is sigma epsilon AS TS to the fourth minus T infinity to the fourth. Okay, so by the way, this here is Stefan Boltzmann constant. It's always equal to 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. Epsilon is the surface emissivity. That's always between 0 and 1. Okay, and AS is the surface area exposed to for radiation. Okay, so there's a bit of a complication though, right? We can't just take this as 1 over our resistance because we have here to the fourth power. Right? These temperatures are the fourth power. So how do we deal with that? Well, again, remembering that resistance is just a useful tool for us. It's kind of a conceptual tool for us. So we often don't care about being 100% precise. We can kind of do a little trick with this. So we can say, well, this is same thing as sigma epsilon AS times, if we factor this out, factor out this expression, we end up with TS squared plus T infinity squared times TS plus T infinity times TS minus T infinity. Okay, if you don't believe me, you can do it yourself. We factor it out and we end up with that. Okay, this is actually kind of looks like a resistance, right? If you squint, right? This kind of looks like 1 over R rad. The obvious thing though is like we have the driving potential as a function of TS and T infinity, and those appear in the resistance as well. So the resistance itself is not independent of the temperatures of the material or the temperatures that are involved. That turns out to be kind of okay if a couple of things. One, if TS and T infinity are approximately equal to each other, right? Then it's okay. The other thing is it's always okay if you just give it a guess, calculate the resistance, then calculate Q dot and your temperatures, and then go back and update your guess and do an iterative process. Like, then that's always okay. So if the point is just to get it kind of a handle on things, as long as your guess is about right, you're going to be okay. And in fact, this is the exact solution up here. There's another way of writing it. That's an approximate solution. So our rad is approximately equal to 1 over sigma epsilon AS times, let's see. So if you look at this is approximately equal to 2 T bar squared. So T bar being the average of TS and T infinity. And this is approximately equal to just T bar, 2 times T bar, right? So if we multiply that together, we can say, well, this is approximately the same as 4 T bar cubed. Right? Again, T bar is the average of those temperatures. So if you really want to be approximate, turns out most of the time this is okay. Usually within like 10% error on a lot of these, unless the temperatures are really, really different from each other. So you can calculate the radiation resistance this way and use it to compare for your problem. Okay, any questions on this stuff? Okay. All right, so the last thermal resistance we'll talk about is contact resistance. Okay, so normally let's say we have these two materials, right? One material has high conductivity, one material has low conductivity. And if we were to plot what the temperature looks like as a function of position here, let's just plot this out. We might look something like this, right? So let's say high conductivity. So first, let's kind of apply the principles we just learned for understanding the problem. So we have a plane wall. So what's the plane wall resistance? That's going to be L over K times AC. For this problem, let's just assume AC is equal to 1, okay? Just for the sake of simplicity. It's not given to us. So we're left with L over K, right? If we have a material with high conductivity, So if K is high, what does that say about the resistance? The resistance is low, right? And so then R is low. Okay, so given a fixed Q dot, right, if Q dot's not changing in the material, here we have a insulation on the top and bottom, right? So Q dot would not be changing. Then our rate equation is TH minus TC over R. So if R is low and Q is fixed, you can bring this over here, right? What does that say about our temperature difference? And so if R is low and Q is fixed, then our temperature difference has to be low as well. Okay, so what I'm saying here is if we draw this out, let's draw this out, we would expect for a material with high conductivity and low resistance that the temperature drop across that material would be relatively low, right? So relatively low temperature drop compared to a material with high conductivity. Okay, so it might look something like this. So just, we don't even have to know anything about the problem other than what we're given and these the idea of resistances, and we can kind of sketch the temperature profile before even solving anything. Okay, so this idea of contact resistance. So contact resistance, which we'll call RC, contact resistance, is normally expressed in terms of an area-specific contact resistance, which is R double prime C, divided by the area available to it for heat transfer, right? So this here would be AC. So let's say we introduce this contact resistance here. Let's maybe sketch out what happens. So at this interface, let's say if you zoom in at the microscopic level, you're going to see there's a very jagged border, right? Like the microscopic level, there's discontinuities in the material, and it's kind of not perfectly aligned. And then the other material next to it is going to be like this. And so you actually, when it comes down to it, you actually have relatively little area that's actually in contact. So all the normal mechanisms of conduction heat transfer are kind of suspended at this point, except for those little smaller areas. In that space between, then you have maybe radiation across, maybe you have conduction through whatever is there. If it's like air or oil or whatever is in that gap, you'd have conduction there. Maybe some convection, although usually the length scales are small enough where that can't occur. But basically there's a penalty for this. Like there's a penalty for not perfect alignment, okay? So if we draw what the temperature profile looks like in this case, so let's see, we've got our new axes here. And we draw the temperature profile. So we would still have conduction across that's relatively low. At this discontinuity though, we would have an immediate temperature drop, right? As a function of position. This here is position. And this is temperature. We have an immediate temperature drop because of this resistance. It's an additional source of impedance to heat flow. All right, and then the rest of the way, you'd have your regular resistance back. Okay. So anytime you have a contact resistance, it just introduces this very local high gradient temperature drop. Okay. So if you look at maybe some specific materials, you could probably go to like an engineering resource for some of this stuff, but in the textbook, this table is given to you. You have things like copper to copper, aluminum to aluminum, and so on. Depending on the clamping pressure involved, the surface roughness, what's between the two materials, the temperature, the effective thermal conductivity can change, right? So the values over here are double prime C.